This is my fourth video in my module on graphing quadratic functions, and in this video we are going to focus on what we call the intercept form of the equation of the parabola. So far we've seen standard form. Standard form is anything looks like this: y equals ax squared plus bx plus c. Got some information on this guy. We know vertex form is anything of the form y equals x minus h quantity squared plus k with the a in front here. The thing I want to point out is that these both have a values and they both behave the exact same way. Well, in this video we say the intercept form of the equation of a parabola is anything of the form y equals a. You can see it up here on the left, but we have x minus, looks like the letter p is the one I adopted here, times x minus q. But a few things I want to say about this: all three of these forms have a values and they behave the same way. So in terms of what I know about this graph, we're going to skip the first two bullet points and head down to the last one and talk about something we already know. But if the graph opens up, that means we have a positive a value, a positive number up front here, and it opens downward if our a value is negative. What else can be said about this form, though, that is very, very convenient is this. We say the x-intercepts are p and q, and notice I say both backwards from what they appear to suggest because of the fact that we have minus signs or negative signs here on our formula or form for these equations. Then we say the p and q are necessarily backwards from what they seem. Okay, so whatever they seem to say, you'll just think they're backwards. And also this: the axis of symmetry is halfway between p comma 0 and q comma 0, and these would be our x-intercepts here, these two numbers p and q. But let's go ahead and take a look at an example here. We can identify a few things. So in this first instance, we say, okay, so I've got an a value of a half. I'm actually going to write that down. I'm going to keep it in our pockets over here on the left. But this would tell us that it opens upward at least. The reason why it opens up is because our a value is positive. Otherwise, it also tells us this: it is wider than y. Well, let's put that down here. Y equals 1x squared, because we have a proper fraction here. It is going to cause our parabola to be wider than what you would normally expect if you had just a 1x squared. Okay. Furthermore, we say the x-intercepts. We want to write these down. So we say x-intercepts. We can write them down as ordered pairs, or we can just write them down as numbers. In this case, though, you see that p and q. I say, what are p and q? And we see a -6 and a -4 with our eyes, but technically we'd say then the intercepts are +6 and +4. So that would mean it hits my x-axis at 6, 0 and at 4, 0, kind of as we've listed above here, p0 and q0. This is 6, 0 and 4, 0. So we say this is very, very true. I also mentioned the axis of symmetry is halfway between p, 0 and q, 0. So we say the axis of symmetry would be x equals, we should write this out as the AOS, at. Now I'm going to write x equals, and I'm going to not write that for just a moment. We're going to go over here to the graph and put our x-intercepts on here just to kind of talk about what this implies. We said we had the knowledge that it hits our x-axis at 4, and it also hits our x-axis at 6. Because of the fact that all parabolas are symmetrical about an axis of symmetry that runs through the middle of it, what we can now say at this point is this. We could say that, well, since those are the x-intercepts, the axis of symmetry, of course, must run perfectly between the two. And so we can now determine that the axis of symmetry must be at x equals 5. Okay? So this is very important when it comes to doing what we need to do next, which is find the vertex. Okay, so in order to find the vertex, here's what we're going to do. We know that the vertex has an x value of 5. That is, the vertex can be written as 5, whatever the y value is at 5. We're going to write it this way. We're going to say 5, f of 5. We are going to need to go find the y value when x is 5. So to find f of 5, we need to plug 5 into our function wherever we see an x. So what I'm going to do is I'm going to take out all the x's in our original rule and put in blanks. And we are going to substitute this 5 in. That's what this asks us to do, is put in the 5 wherever I see an x. And then just go find the y value when x is 5. So we simplify this down to 1/2 times, now 5 minus 6 is -1. 5 minus 4 is +1. So +1 times -1 is -1, and -1 times 1/2 is -1/2. So what this means is the y value when x is 5 is -1/2. So we get this. Our vertex is at 5, -1/2. So the vertex form of a parabola is very, very convenient to sketch from, but intercept form is also not so bad. We know our vertex is halfway between these two intercepts, and we have to just go find the y value. But at this point we could say if that's our vertex, we should label this. We say over 5 down 1/2. down a half. Then here's our upward opening wider parabola. And all we needed to find first were the two intercepts, and they kind of just come out and tell themselves to us. So we're going to try this again with one more quick example. We say, okay, so go ahead and graph this one. Start with this. What's our a value? Our a value. So number out front here, our coefficient is a. We say -1. Okay, -1. This tells us as it's negative that it opens downward. So we say opens down. Opens down. What else? Because the a value, or at least the absolute value of a, is 1, then we'd say, well, then this is going to have a normal width. It just opens downward, but it still has a normal width. Cool. It's not wider, it's not skinnier than 1, it is 1. Furthermore, we could say, okay, so now our x-intercept, since it's in intercept form, always easy to tell that this is an intercept form because of its factored form here. Two factors multiplied together. We say the x-intercepts, there are 2 of them, and they happen to be at -2, -2, and +4 because of our backwards nature of our factors up top there. So here's what we know. We know our graph hits the x-axis at -2. We know it hits our x-axis at +4. That's pretty easy to piece together. Okay. That being said, we know that the axis of symmetry has to be perfectly between these things. So if this is an entire distance here of 6, we'd say, well, half of 6 is 3. If I were to count in 3 this way, 3 this way, or 3 this way, we'd arrive upon this x value right here. But essentially what this does is it implies that our axis of symmetry must have the x value of 1. So we'd say x equals 1 is our axis of symmetry. So to graph the rest of this, all we need to do is plug this into our function. We know the x value is 1. We need to go find f of 1. So f of 1, let's go ahead and do this. We say f of 1 means everywhere I see an x in my function, we're going to take it out and put in a blank set of parentheses. And then we will substitute for all blank sets of parentheses, or all x's, we will put in the value that we're plugging in here, which is 1, and go find the y value. So we end up with this. We say negative, in this set of parentheses, 1 plus 2 is 3. 1 minus 4 is -3. So essentially we get -3 times -3 is 9. So what this means is our vertex is at 1, and then it is at a y value of 9 when x is 1. Okay, so we have this here as our vertex. So our vertex at 1, 9, we say go over 1 up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here she is, right here. And then from here, we should label this. We say 1, 9. We can sketch in the rest of our parabola. Kind of freehand, so just kind of be careful here. That's not a very good one if you ask me. It needs to get steeper and steeper like that, at that kind of ish. Okay, but this is our parabola, and so intercept form of a parabola is very, very nice, or of a quadratic is very nice because it just tells you the intercepts, and then you can find the axis of symmetry, which leads you to the vertex. Cheers.